Hello, everybody. We're going to go ahead and get started with today's lesson. So, today we are going to talk about sample spaces, probability, and counting. So, the first thing we need to discuss is an experiment. So, an experiment is a situation involving chance that leads to results, and we call those outcomes. So, this is a little bit different than a scientific experiment. We're working with kind of a mathematical experiment. So, an outcome is a result of a single performance or trial of an experiment. So, an outcome, and we're just talking about one single trial of an experiment. An event is one or more outcomes of an experiment. So, this is what could occur. The sample space is the set of all possible outcomes. So, and we can represent a sample space in a couple of different ways. We can use an organized list. We can use a table. Or we can use a tree diagram. So, if we're talking about a coin that is tossed twice, we want to represent the sample space, so all possible outcomes for this experiment by making an organized list, a table, and a tree diagram. So if we're talking about an organized list, let's say we flip the coin the first time. One option is that we get heads on that very first flip. And then we flip it again, and we get heads again. Now, we could also get heads on that first flip, and then we could get tails on the second one. Okay. Now we could also say, okay, well, what happens if I get tails on the first flip? Well, I could get tails on the second, but I could also get tails on the first flip, and I could get heads on the second. So this would be our sample space because this is all possible outcomes of this coin flip. We can also represent this as a table. So again, these are all of our outcomes. And our two options for that first flip are heads and tails. But then our two options for that second flip is also heads and tails. So what we fill in these boxes is that sample space. So again, first flip is heads, second flip is heads. First flip is heads, second flip is tails. First flip is tails, second flip is heads. First flip is tails, second flip is tails. So again, this is that first flip, and these are representing that second flip. So this is another way to represent it. Okay, so we can also do this as a tree diagram. So all of our outcomes, our first option is heads or tails, right? That's our first flip. This is our first toss. But then for that second toss, we have kind of two more options, right? For the first heads, we have heads or tails. And then for the second one, we also have heads or tails. So this is representing the second toss. And then we would write our sample space as, okay, first flip was heads, second flip was heads. First flip was heads, second flip was tails. First flip was tails, second flip was heads. And first flip was tails, second flip was tails. So this is representing that sample space, which again is all those possible outcomes. So these are kind of three different ways to organize our experiments and our outcomes. And you can kind of pick whichever one you feel most comfortable with. But we're going to go ahead and we'll do it again. So this one says a coin is tossed and then a number cube is rolled. Represent the sample space for this experiment by making an organized list, a table, and a tree diagram. So that cube is going to be 1 through 6, right? We're just talking about like a 6-sided dice. And so we'll start with our organized list. Well, I could flip a coin and get heads. And then I could roll that dice and get 1. I could flip a coin and get heads and then roll the dice and get 2. Flip a coin and get heads, roll the dice and get 3, and so on and so forth. Heads and then a 5, heads and then a 6. And I have to stop there because that's the highest number on the dice. And so that's kind of half of my list, but then I could also flip a coin and I could get tails. And then I could roll a dice and get 1. I could get tails and 2, tails and 3, and so on and so forth. These are all of those possible outcomes. Okay, so that's it represented as an organized list. Now I can also represent it as a table. Ooh. Honestly shocked that kind of worked. Okay. So as a table, we'd have to kind of draw our table here, right? I'm going to do the heads and the tails actually as the rows this time. So again, our 2 options are heads or tails. These are all of our outcomes. And then our options for the dice are 1, 2, 3, 4, 5, and 6. Okay. So again, to write that sample space, we have heads and 1, heads and 2, heads and 3, heads and 4, heads and 5, heads and 6, now we're on tails. Sorry about that. Tails and 1, tails and 2, tails and 3, tails and 4, tails and 5, and tails and 6. So again, we're getting all of those same values from that organized list. We're just representing them in a different way as a table. So you kind of can have your own preference for this. And then we are also going to represent it as a tree diagram, which you may need to write a little small for this one because it's going to get a little bit bigger. So again, we have our outcomes. That's what we're trying to find. And the first thing we're trying to do is okay, heads and tails. Heads and tails. Because, right, what we're doing first is we are tossing a coin. So this is representing that toss. Okay. Heads or tails. And then from that heads or tails, we have 6 more options, right? I can toss and I can get a 1, I can get a 2, I can get a 3, I can get a 4, I can get a 5, and I can get a 6. And I can do the same thing on tails, right? I can toss and get a 1, toss and get a 2. Roll and get a 2, roll and get a 3, roll and get a 4, roll and get a 5, roll and get a 6. So this is representing that dice roll. And now our sample space would kind of come down from those. So again, this would be heads and 1. This would be heads and 2. This would be heads and 3. Heads and 4. Heads and 5. And heads and 6. This would be tails and 1. Tails and 2. Tails and 3. Tails and 4. Tails and 5. And tails and 6. So again, this is representing that sample space. But from all of these, we're getting the exact same thing. So this is just different ways to represent the same thing. And a list, a table, or a tree diagram. Alrighty. So we can have different types of experiments. So this is just introducing us to an experiment and how we can get outcomes from that experiment. Now, we can also have 2-stage experiments, which a 2-stage experiment is an experiment with 2 stages or events. So we've actually kind of already done this a little bit, right? Before we had 2 stages or events. So that first one was a coin toss. That was our first event. And then another coin toss. That was our second event. Whereas in that part B, we had a coin toss. That's our first event. And then we had a dice roll. That's our second event. So we kind of already have done the two-stage experiment, but we can also have multi-stage experiments, which is an experiment with 3 or more stages or events. So to take a hamburger, so we're going to do an example of this. To take a hamburger order, Kendra asks each customer the questions from the script shown. Draw a tree diagram to represent the sample space for hamburger orders. The sample space is the result of the 4 stages. So we're looking at this image. So the first one is, what size would you like, kids, regular, or large? So that would be our first stage, is determining the burger size. And we'll kind of abbreviate that: kids, regular, or large. Okay. The next one is, would you like cheese on that? So we have 2 options: cheese or no cheese. Okay. Then it says, would you like tomato and or pickles? So that's actually 2 stages, even though it's one question, right? Because one of them is going to be tomato, which is tomato or no tomato. And one of them is going to be pickles, which is pickle or no pickle. Alrighty, so we have a 4-stage experiment. So this is a multi-stage. Again, there's space here, but be really careful. You may have to kind of write small because there is going to be a lot of ones here. So we, again, are trying to find our outcomes. Okay, so first step is burger size. I might write this differently. I think I'm going to switch this, actually. I'm going to put outcomes up here. Okay, so first step is burger size. So we have 3 options. Right? Okay, so we have the kids, we have the regular, and we have the large. Okay, or I'm actually going to abbreviate these just so that when we get to that sample space, we have just kind of working with some variables. So we have kids, regular, and we have a large. So the next step for each of these is cheese or no cheese. So again, we're spanning off of both of these: cheese or no cheese. Okay. So we have cheese or no cheese. And then from each of those, we have tomato or no tomato. So each of these are going to get tomato or no tomato. Tomato or no tomato. Tomato or no tomato. Tomato or no tomato. And so on and so forth. And even further than that, each of those is going to get pickle or no pickle. So each of these get pickle or no pickle. Pickle, no pickle, pickle, no pickle, pickle. Okay, so we should see all of our stages here, right, or events. Our first one is that size, right? And then we determine the cheese. And I'm going to move this so I can kind of scoot you in a little bit. And then we have the tomato stage and the pickle stage. So then the last thing we need to do is we need to write our actual sample space. And this is where it gets to be a bit of a lot, right? Because what our sample space will be is for this first one, again, we chose kids with cheese, tomato, and pickle. And then we chose kids with cheese, tomato, no pickle. And then we chose kids with cheese, no tomato, and a pickle. Kids with cheese, no tomato, no pickle. You see how it starts to kind of run into one another? So that's why we do have to be careful. There's only so much space kind of on here. So it will take a little bit of kind of finagling to make this work. So then we have here, we do kids. This is no cheese, tomato, pickle. Kids, no cheese, tomato, no pickle. Kids, no cheese, no tomato, pickle. Kids, no cheese, no tomato, no pickle. Okay. So, as we can see, there are tons of options, and that makes sense because of what this sample space is. So, we do have to keep going in order to kind of get all of our options. So now we're moving on to the regular, and it's kind of all the same things, right? This is regular, cheese, tomato, pickle. And then we have a regular cheese, no tomato. I'm sorry, cheese, tomato, no pickle. Then we have regular cheese, no tomato, pickle. And then we have regular cheese, no tomato, no pickle. Then we have regular, no cheese, tomato, pickle. Regular, no cheese, tomato, no pickle. Regular, no cheese, no tomato, pickle. Regular, no cheese, no tomato, no pickle. All right, so that gets us through the regular, and then again, we do the same thing, but for the large. So we have a large cheese, tomato, pickle. A large cheese, tomato, no pickle. A large cheese, no tomato, pickle. A large cheese, no tomato, no pickle. Large, no cheese, tomato, and pickle. A large, no cheese, tomato, no pickle. A large, no cheese, no tomato, pickle. And a large, no cheese, no tomato, no pickle. Alrighty, so that's our whole list. And what that is representing is the sample space. So again, all of those possible outcomes are here, this sample space. So we have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. We have 24 different options for how we could make this sandwich. And we see that from the sample space. We see that from all of the options listed. And so this is how we would write out that multi-step experiment. Alrighty. So then we're going to kind of switch gears and we're going to go to the fundamental counting principle. And so the fundamental counting principle is a way to find the number of possible outcomes. So up until this point, we've had to kind of write out our sample space to figure out the number of possible outcomes. And we have to admit that doing that was a lot. It's good to see what all of our possible outcomes are, but when we get into more complicated experiments, we don't want to have to do that for every single one, especially when we start getting into 6, 7, 8 stage experiments. So we can instead use the fundamental counting principle to figure out, okay, how many different options do I have? And we find that by multiplying the number of possible outcomes from each stage or event. So what does that mean? So let's say we're looking here. We have Haley has selected a size and overall style for her class ring. Now she must choose from the ring options shown. How many different rings could she create in her chosen size and style? So we're trying to figure out, okay, well, how many rings could she create? Well, the way that we find this is we would say, okay, well, she has 10 medals to choose from. So she could choose 10 different medals. And then from each of those medals, she could choose 2 different finishes. From those 10 medals and 2 finishes, she could choose 12 different stones. She could choose 5 different cuts. She could choose 20 different activities, 20 different logos, or 20 activities for one side, 20 activities for the other. And there are 2 different band styles. So these are all of her options. So when we multiply all of those together to get the total number of options possible, we should get 960,000 rings. So, and again, that's operating using that fundamental counting principle. We're multiplying the number of different outcomes per stage. And we can see that that would work for the previous one, right? We said that we had 24. Well, in that first stage, we had 3 options. In that second stage, we had 2, and then we had 2, and then we had another 2. 3 times 2 is 6, times 2 is 12, times 2 is 24. And that lines up with how many we did end up having. So that is what this fundamental counting principle represents. Alrighty, so we want to find the number of possible outcomes for each situation. So the first one is the answer sheet shown. So if we complete it, what are the number of different outcomes? Well, for the first question, we have 4 different outcomes, right? We can pick A, B, C, or D. Those are all of our different options. And then for the second question, we also have 4, right? A, B, C, or D. We have the same for the third, the fourth, the fifth, and the sixth, right? All of those have 4 different options. But then we get to the 7th problem and we start seeing, okay, well, there's actually only 2 here. So for this stage, instead of multiplying by 4 options, we really only have 2. And we also have 2 for 8, 9, and 10. Right. So this is treating each question as a separate stage of an experiment. So they're all separate, and this would give us our possible outcomes, which should give us 65,536 outcomes when we calculate it. Yes. Okay. So this next one is totally separate. It says a dot cube is rolled 4 times. So again, this is talking about just like a normal number cube, 1 through 6, if you're rolling a dice. Well, on that first roll, we have 6 outcomes, right? We have 1 through 6. On that second roll, we still have six outcomes. We have 6 outcomes on the third and 6 outcomes on the fourth. And so that would give us the total number of outcomes that we would possibly have, which is 1,296 outcomes. Okay. I'd like you to try 3 on your own. All right, so this says a pair of women's shoes come in sizes 5 through 11 in red, navy, brown, or black, and they can be leather or suede and are available in 3 different widths. So the first kind of stage is size, right? 5 through 11. So that is 7 different sizes. And it says whole sizes, so we're not doing like 5.5, 6.5, whatever. 5, 6, 7, 8, 9, 10, 11. That is 7 different sizes. The next stage, it says it can come in red, navy, brown, or black. So that's representing 4 different color options. And then they can be leather or suede. So that's representing 2 different material options. And then finally, they said they're available in 3 different widths. So that would be 3 different widths. So this would be our setup for that problem to see all the possible outcomes. And then we would multiply those together and do 7 times 4 times 2 times 3. And we should get that there are 168 options. Okay. So next thing we're going to talk about is unions and intersections. So unions represent the set of all outcomes of two events that are in either event. Okay, so this is represented as A union B. So what does this mean? So this first picture is representing A union B. And so union is saying, okay, well, you could be in event A, or you could be in event B, or you could be in both of them. So it's representing everything that's going to meet these two criteria. So let's say like A is you play soccer and B is you play basketball. Well, if you played soccer or basketball or both, you would fall in that intersection, or I'm sorry, that union. Now there's also the intersection, which is the set of all outcomes of two events that are common to both events. And this is represented by A intersection B. Okay, so this is saying, okay, again, if A is you play basketball and B is you play soccer, this is saying you would have to play basketball and soccer in order to be considered in this. So a union is saying, okay, everything. I don't care if you play basketball, soccer, or both, I'm going to include you. A intersection B is saying you got to play both. So in an experiment with equal likely outcomes, the probability of event E is the ratio of the number of outcomes in the event to the number of outcomes in the sample space. Here we're talking about probability. So probability, which we write as P of, we're going to say E representing some event. So again, that you play soccer or something like that. So the probability that something happens is going to be the number of outcomes of that event, right? So the number of outcomes of the event over the number of outcomes in the sample space. Or we can say the number of outcomes possible. Okay. So we're going to kind of do this real quick. So a spinner is divided into 8 equal sections that are numbered 1 through 8 as shown. Let A be the event that the spinner lands on an event number. Let B be the event that it lands on a number. Let A be the event that it lands on an even number. Let B be the event that it lands on a number between 5 and 8 inclusive. Construct a Venn diagram and answer the following. So we're going to start by constructing a Venn diagram. Okay, so we have two options. We have event A, right, which is that it's going to land on an even number. And then we also have event B, which is that it's going to land on a number between 5 and 8, inclusive, meaning it could be 5 or 8. Okay, so we want to fill out this diagram. So 1 is an odd number, and it's not between 1 and 8, so it's going to be out here. 2 is an even number, but it's not between 5 and 8, so it's going to be here. 3 is an odd number, and it's not between 5 and 8, so it's also going to be out here. 4 is an even number, but again, not between 5 and 8, so it's going to go here. 5 is an odd number, but it is between 5 and 8, so it'll go here. 6 is an even number and between 5 and 8, so it'll go in the middle. 7 is an odd number, so it's not going to be an A, but it is between 5 and 8, so it'll go here. And 8 is an even number between 5 and 8 inclusive, so it'll go there. So this would be representing that Venn diagram. So now we're going to answer the following. So this says find A union B. So again, A union B is saying, okay, you can be in A, or you can be in B, or you can be in both. So what this means is, okay, well, 2 is an A, so that's going to be included. 3 is not an A or B, neither is 1, but 4 is in A, so we'll include that. 5 is in B, so we'll include that. 6 is in both of them. 7 is in B, and 8 is in both of them. So it's saying as long as it's in one, we're good to go. So this would be our A union B for this problem. So then it says find the event that event A or event B will occur. I know I'm missing T's here. Okay, so we want to find the probability. So it says find the probability that event A or event B. Again, that's representing A union B. It's saying you can be in A, you can be in B, you can be in both. As long as one of them occurs, that's what we're worried about. So we would take the number of outcomes in that union and we would divide it by the number of outcomes possible. So the number of outcomes in that union, we have 1, 2, 3, 4, 5, 6. 6 possible outcomes that work in that union. But we have a spinner labeled 1 through 8. So we have 8 possible outcomes overall. So that means our probability that it is in that union is going to be 3/4. Alrighty. So this says the Venn diagram shows members of two sports teams who serve on the student council. One of the students will be chosen at random to attend a meeting. Let A be the event that a student plays basketball, and let B the event that a student plays tennis. So we want to find the intersection. So this time we're only worried about students who play basketball and also play tennis. So we want to figure out their intersection. So we're talking about just that middle piece here. So our A intersection B would be represented by Meg and Ed because they both play basketball and tennis. Not just one or the other or both, just both. So then it says, what's the probability that the student who's chosen plays both basketball and tennis? So again, we're trying to find the probability that they play both, or the probability of A intersection B. So again, we find that by the number of number of outcomes in that intersection over the number of outcomes possible, which the number of outcomes in that intersection is just 2, right? There's 2 people who play both of those. But there's 1, 2, 3, 4, 5, 6, 7 different outcomes total because there's 7 different people included in this. So this would be our probability 2/7. Okay. A standard cube is rolled. Let A be the event that the number is greater than 3 is rolled, and let B be the event that an even number is rolled. So, again, we're trying to find the intersection. So I'm actually not going to draw a Venn diagram for that. Let's think about this. So we're rolling a standard number cube. Again, this is 1 through 6. We want to find the event that the number is greater than 3 and also that it is even. Okay. So starting off the bat, we know that we want it to be greater than 3. So I can ignore 1, 2, and 3. Okay, so then we get to 4, and we want to say, okay, well, 4 is bigger than 3, but is it an even number? Yes, it is. So it would be in this intersection because it meets both of these requirements. Well, 5 is a number bigger than 3, but is it an even number? No, it's not. So it is not going to be in this intersection. And then 6 is a number bigger than 3, and is that an even number? Yes, it is. So again, in order to be in that intersection, it has to meet both of those requirements. And then it says, what's the probability of rolling a number that is greater than 3 and even? So what's the probability of that intersection? So again, it's going to be the number of outcomes in that intersection, which is 2, over the number of possible outcomes. Well, there's 6 outcomes when you roll a cube. So our probability is 1/3. All right, this is the last thing for today, which is the complement. So the complement of event A consists of all the outcomes in the sample that space that are not included as an outcome of event A. Okay, so when we say the complement, we're talking about, okay, everything else. So for example, this says when a standard number cube is rolled, the probability of rolling a 4 is 1/6. What's the probability of not rolling a 4? So if we're trying to find the probability of not rolling a 4, not 4, probability is always going to be kind of like a decimal. So what we can do is we can say 1, which would be the probability of basically everything, and we would subtract the probability of rolling a 4. So we'd say 1 minus the probability of rolling a 4, which we know to be 1/6. We can rewrite 1 as 6/6 to help us subtract. And so our probability is going to be 5/6. The probability of not rolling a 4. So this one says Francesca bought 200 raffle tickets hoping to win a $100 gift card to her favorite clothing store. If a total of 300 raffle tickets were sold, what's the probability that Francesca did not win the gift card? So again, the way we do this is we say, okay, well, the probability of her not winning is going to be 1 minus the probability of her winning. So the probability of her winning is her 20 tickets out of those 300 winning something. So we would do 1 minus 20 over 300 in order to get the probability of her not winning. So that fraction actually reduces to 1 over 15. And again, we can rewrite 1 as 15 over 15 to help us subtract. And so our probability would be 14 over 15 of her not winning. Alrighty, and that is it for today. So go ahead and work on your homework.